So sorry for running a little bit late. We were having some technical problems. It is a pleasure to have Dr. Khan with us today. He received a PhD in biotechnology in 1996 in Al-Ghira Muslim University in India, institution where he is currently a professor. His research areas of interest are protein structure and function, protein misfolding or aggregation, and amyloid induction and inhibition. He has published hundreds of papers and participated in several journals as editor, as well as visited the States, Arabia Saudi, and the UK as a research fellow. So in case you are interested to check his full research activities, you can use his ORCID code, which was provided within the IBB seminar information that you all received. So I would like to thank you, Khan, for your interest in IBB and for offering yourself to give us your talk about amyloid induction and its inhibition. So if you want to start, you can do it now. Thanks a lot.
Okay, thanks for the nice introduction. So I'll be speaking on the protein aggregation and its inhibition. So let us start with the introduction part. Sorry. We don't know. It's not moving. Okay. Yes.
Yeah, we can see it. You can.
Okay. Sorry for this disturbance. So anyway, so once the protein that is going to get synthesized on a ribosome, it's going to fold properly and it's going to perform a normal function. But in some cases, you'll be getting the misfolding of the protein, and in that case, there will be the loss of the function. If there is the overproduction or there is a formation of the sticky patches, that may lead to the formation of the aggregates of the protein, and this is going to gain a toxicity. And this leads to neurodegenerative disorder. The protein which is going to not fold properly, or if it's going to have a mutation, so it's going to recognize by the proteasome, and they are going to be degraded into peptides and free amino acids. Now, the first question that we have asked that if we take alpha class of protein, beta class of protein, or random, so can we induce the amyloid fibril formation by using the SDS? So this is the first question that we have asked. And this is a study that is being published in PLOS One in 2012. So the technique that I'm going to use in my presentation, that is Rayleigh scattering, that is fluorescence based, where we are supposed to excite at 350 nanometer and take the emission at 350 nanometer. Turbidity measurement, this is spectrophotometric based. And these are the two dyes which are being used for the characterization of the amyloid TST binding assay and Congo red. CD measurement is being performed just to characterize the formation of the beta sheet structure, which is going to give a negative peak that may be confined around between 210 to 228 nanometer. Transmission electron microscopy to study the morphology of the protein aggregates. Now, this is a basic slide. Here you can see the protein, they are made up of different number of positive and negative charge amino acid residue. Positive like histidine, arginine, and lysine, negative aspartic acid and glutamic acid. And each protein, they have unique isoelectric point. So if we are going below isoelectric point, so in that case, the protein, it's going to acquire a overall positive charge. And if we are going above pi, so in that case, the protein is going to acquire a overall negative charge. So these were the 25 different proteins that were taken in our study. These proteins, they belongs to alpha class of protein, which include human cerebroalbumin, valbumin, fatiguin, acylfetrin, glucose oxidase, invertase, alpha lactalbumin, alpha amylase, and conalbumin. All these proteins, they belongs to alpha class, and alpha plus beta, that is lysozyme and hemoglobin, and beta class of protein, that is CONA, cobra toxin, beta lactalbumin, bovine liver catalase, chymopapin, right IgG, and bananaractin. Only one protein that is being taken, it's a random call protein, that is a gelatin. So these were the different proteins that were being taken. Once the protein that is being synthesized in the cell, so it's going to come into close contact with the plasma membrane, which is made up of the phospholipids. And phospholipid, it will be having a hydrophilic head and hydrophobic tail. Keeping this point in our mind, we have taken a SDS. SDS is a negatively charged head group. So here you can have a negative charge. Here is also its negative charge. 12 carbon long hydrophobic tail, and it's having a CMC. It's around 8 millimole. And this mimic the characteristic of biological membrane. Now coming to the result part. Now my presentation that will be rely on these techniques like Rayleigh scattering, turbidity, TST, CD, and TEM. Now here we have measured the Rayleigh scattering by taking 25 different proteins. Each protein, they were being taken at 5 micromoles at neutral buffer. So these proteins, they don't contribute any Rayleigh scattering. While once we take protein 5 micromoles 2 unit below pi, even in that case also we won't get any positive Rayleigh scattering. Once we take a protein 5 micromoles 2 unit below pi along with the 500 micromoles of the SDS, in that case, irrespective of the classes, all the protein, they show positive Rayleigh scattering. While the protein which is being taken 2 unit above pi, so that also doesn't show any positive Rayleigh scattering. So only one condition that is going to show a positive Rayleigh scattering is that where we take a 5 micromole protein 2 unit below pi along with the 500 micromoles of the SDS. Now the turbidity measurement that were being also being performed by taking a different proteins which were being shown on the x-axis under the condition 5 micromoles 2 unit below pi and 500 micromoles of the SDS. So all of them, they show a positive turbidity measurement. Then we have performed the TST measurement just to characterize whether these proteins, they are forming a amyloids or not. So here you can see the green one where we have taken a 5 micromole protein 2 unit below pi along with the 500 micromoles of the SDS. So all of them, they show a positive TST binding. Now this is the CD measurement that is being performed. This is at neutral buffer. So if the alpha class of protein is there, so you'll be getting a 2 negative peak. If it is a beta, so 1 negative peak, that will be around 214. And this is the random coil. And all these spectra, they were being taken 2 unit below pi. So there was no significant change in the spectral property that were being observed once we are going to take all the protein 2 unit below pi. But once we take all these protein 2 unit below pi along with the SDS, so in that case, we get the formation of the beta sheet-like structure, where we get a negative peak that may be around between 210 to 225 nanometer. So this indicates that only one condition, that is 2 unit below pi along with the SDS, that shows a formation of the amyloid structure or the beta structure also. Here it's a tabular form that is being shown. Now here you can see all the protein, they are being, once it is being taken at PS 7.5. So you can see the amount of beta structure. And 2 unit below pi, so there was no significant change in the beta structure that was being observed. But once we take 2 unit below pi along with the SDS, so you can see from 8 to 47% there is an increase. Likewise, in all the cases, we get the increase in the beta sheet content. Now these are the TEM images that are being shown. Now these are from the different classes like alpha, alpha plus beta, and the random structure protein. All the protein, they show a clear amyloid fibril formation. Now this is the overall scheme that is being shown. Now we have taken alpha class of protein, beta class of protein, alpha plus beta random. And the condition that we have taken, that if we are going 2 unit below pi, so in that case, the protein, it's going to acquire a overall positive charge. And this SDS, which is having a negative charge head group over here, it's going to neutralize this charge, and this may facilitate the formation of the amyloid. While on the other side, if we are going 2 unit above pi, so in that case, the overall charge on the protein, it will be negative. And because of the negative, this anionic detergent is there, so there won't be any interaction. There will be a charge-charge repulsion, and this is not going to favor the formation of the amyloid. So from here, we can conclude SDS have a great potential to induce amyloid fibril formation when protein are subjected to 2 unit below pi. Both electrostatic as well as hydrophobic interaction are responsible for amyloid fibril formation. Now, the second question that we have raised, from the first chapter, it's clear that the thing that is required, that we should go below pi, and then the protein that is going to acquire a positive charge, and if we are going to add an anionic detergent, so in that case, we get the formation of the amyloid. Now, in the second hypothesis, what we have done, we have fixed the protein, we have fixed the detergent, anionic detergent. Now, by changing the pH, we can manipulate, we can increase the charge on the protein. And the protein that is being taken, it's a lysozyme, because it's having a pi that is around 11. So now here, what is the hypothesis that we are giving, that if somehow the charge on the protein will be more, and if we are going to add the same amount of the SDS, so in that case, whether we get more amyloid fibril formation. So this is the question that we have raised. Now, this is a study that has been published in Soft Method in 2014. Now, the protein that is being taken, it's a hen-egg lysozyme. This is alpha-beta class of protein. And here, the only important point is that is regarding our presentation is this protein is having a pi that is around 11.2. Now, coming to the result part. Now, the charge on the protein that is being calculated by a protein calculator 3.3. So here you are supposed to give the amino acid sequence to the feed the amino acid sequence to the computer, and by just give the different pH value, and you can determine the charge on the protein. So here you can see this is a near about isoelectric point. So here the charge that will be around 0. As we are going to go below pi, so the charge on the protein that is going to get increased. So at the end, I'll discuss that these 2 points that will be important for the discussion part, that at pH 9, the overall charge that will be around 9, and at pH 1, it will be having a 19 positive charge. So in a simple way, what we can say, as we are going to lower the pH from 11 to 1, the positive charge on the protein that will keep on increasing. Now, here we have measured the Rayleigh scattering, and the protein concentration that is being taken 15 micromoles of the lysozyme, and we just want to standardize what is the concentration of the SDS that is needed to get a maximum Rayleigh scattering. And this is the experiment that is being done at pH 7. So from here you can see that the maximum Rayleigh scattering that is being observed at 0.3 millimolar concentration. So for the rest of the experiment, we are going to fix the 15 micromolar concentration of the lysozyme and 300 micromolar concentration of the SDS for the rest of the experiment. So now here you can see we have taken 15 micromoles of the SDS lysozyme and 300 micromoles of the SDS, and we have varied the pH, observed the Rayleigh scattering. So here you can see this is the isoelectric point. As we are lowering the pH, so the Rayleigh scattering that is going to get increased, and Rayleigh scattering that is being observed at pH 1. So here we have observed the kinetics. Hyperbolic curve that is being observed at pH 1, followed by pH 2, followed by pH 3, 5, 7, and you can see it's going to steep off. There is no change in the kinetics, Rayleigh scattering at pH 8 and 11. So from here again we can say that at pH 1 we are getting the maximum Rayleigh scattering as well as the steep hyperbolic kinetic curve in terms of the Rayleigh kinetics observation. Now the second thing is we observe the turbidity. We have also taking the blank, but I'll skip that because of the shortage of the time. So you can see 15 micromoles along with the SDS, and the turbidity is being measured. So it's almost a similar pattern as we observe in the Rayleigh scattering is being observed in the turbidity also. And we get a maximum turbidity at pH 1. Now this is another experiment which is being done with respect to the TST binding. And here you can see, as we are expecting that we should get a maximum TST binding at pH 1, but we were not getting. The reason is the TST myocyl, they get disturbed at very low pH, and it is because of that maximum TST binding, because some dye, they are sensitive towards the pH. It's a similar case for the Congo red also. Now this is the another dye which is being used for the characterization of the amyloid. Now you can see this is the observation that is being made at pH 7, and this is at pH 5. Now you can see this is in the absence, and this is in the presence of the this SDS, and you can see there is a red shift that is taking place at pH 7 as well as pH 5. Now here you can see this is the summarized data that is being shown over here. As we are going towards the lower pH, so the amount of the red shift is going to be getting increased, and it is found to be maximum at the lower pH end. Here also we cannot go beyond pH 5 because this type is going to lose the color. Now the CD measurement that is being performed, these are some representative spectra that are being shown at pH 1, 3, 5, and 7. So this is the alpha beta class of protein, and this is in the presence of the SDS. You can see all the protein, they are going to adopt a beta sheet-like structure. Now these are the time images at pH 9, 6, 3, and 1. At pH 1, you can see there is it's more dense amyloid fibril formation that is taking place. Now again, this is the summary of the work. This is a lysozyme which will be having a 9 negative and 17 positive charge. At pH 9, as I said, it will be having overall 5 positive charge, and the stoichiometry of the SDS that is being taken is 1:20. Now here you can see it's only 2 bundles of the amyloid that are being formed. And here you can see it's at pH 1. The lysozyme, it will be having a overall 19 positive charge, and is under the same stoichiometry, it is going to lead to the formation of the more amyloid. While on the other side, if you are going above PI, that is above pH 11, so in that case the protein, it will be having overall negative charge, and negative charge is not going to interact with this, and we won't get any amyloid fibril formation. So from here again, we can conclude that the aggregation is found to be maximum at pH 1 because of the net positive charge was maximum at pH 1, and SDS interact both electrostatically as well as there is a hydrophobic interaction also there. Now from the first chapter, we have determined that irrespective of the classes, whether we take alpha class of protein, beta class of protein, alpha plus beta, or random, only one condition that is required: we should go below PI of the respective proteins, and then if we are going to add the SDS, so in that case we get the formation of the amyloid. In the second hypothesis, we have proved that we have fixed the protein, we have fixed the detergent. Only thing is, by changing the pH, we have manipulated the charge on the protein, and as we are going towards the lower pH side in the lysozyme, below the PI, so in that case we are going to get more and more positive charge and more amyloid fibril formation that is taking place. So till now we haven't discussed about the role of the hydrophobic chain length. So now here what we have done in the third hypothesis, we have taken 5 different serum albumin, and we have taken a fixed negative charge, but we have varied the chain length of the detergent, like 12 carbon chain length in the SDS, 18 carbon chain length in the SDBS, and 20 carbon chain length in AOT. And this is a study that is being published in Physics, Chem Physics in 2014. Here we want to show prove that whether there is any role of the hydrophobicity or not. So these were the 5 albumins that were being taken, and all the albumin, they will be having a PI around 5.6, or you can say approximately 5.5. And these are the structure of the detergent. This is the SDS, which is 12 carbon. This is SDBS, which is 18 carbon chain length, and this is the AOT, which is 20 carbon chain length. And all of them, they have a negative head group. Now coming to the result part, Now, again, we'll go by this table. We'll discuss Rayleigh scattering, turbidity, TST, congruent, and CD and TEM. I'll explain one figure because here the similar type of result that are going to be observed in the rest of the 4 albumins also. So as I said, I have taken 5 albumins. So this is HSA, human serum albumin, and it is a Rayleigh scattering that is being observed. So here you can see in the case of SDS and SDBS, the Rayleigh scattering that get increased and then it slopes off around 3 millimole. While in the case of AOT, that remain persistent even up to 11 millimole. And similar pattern that is being observed for the BSA and other 3 proteins like PSA, SSA, and RSA. So this is about the Rayleigh scattering. Now, kinetics also being observed by the Rayleigh scattering, and you can see again it's a very steep hyperbolic curve that is being observed for the AOT, followed by the SDBS, then SDS. A similar pattern that is being observed for BSA, PSA, SSA, and RSA. Now, the turbidity measurement that is being performed, and here also we got almost a similar observation that in the presence of the AOT up to 11 millimole concentration, we get a positive turbidity for all the 5 albumins like PSA, SSA, and RSA. Then we have performed the congruent. Again, you can see the congruent binding was also found to be persistent as we observe the Rayleigh scattering and turbidity for the 5 albumins. So this is HSA, this is BSA, PSA, SSA, and RSA. Now the congruent binding that is being shown, this is in the absence and this is in the presence of the SDS, SDBS, and AOT. You can see that the peak is going to shift towards the right hand side. That indicates there is a red shift that is taking place in the presence of all these 3 detergents. Now this is the CD data that is being shown. Now you can see in the presence of the SDS, 2 millimoles of the SDS, SDBS, and AOT, these protein, they are going to adopt a beta sheet-like structure in all the 5 albumins. Now these are the TEM images that are being shown. The upper panel is for the BSA and the lower panel is for the HSA. This is in the presence of the SDS, this is in the presence of SDBS, and this is in the presence of the AOT. And in the presence of AOT, you can see there is a maximum dense amyloid fibril formation that is taking place. Now, this is the summary of the work. So, as I said, we have taken a 5 albumins and the experiment that were being performed at pH 3.5. The reason is the isoelectric point of all these albumin, it is 5.5 or 5.6, and all the 5 albumins, they have been taken 3.5, and from the literature it is being known that this form is known as, and here what we are interested in, that the protein is going to acquire a overall positive charge. And if we are going to add from 0.5 to 2.5 millimoles of the SDS, so in that case we get the amyloid fibril formation. This is 12 carbon chain length. Now this is 18 carbon chain length. Now you can see it's a schematic presentation again. Now instead of 2, there are the 3 bundles they are being shown under the similar condition. While in the case of AOT, we observe that there is a persistent TST binding and Rayleigh scattering that was being observed from 0.5 to 11 millimole. So in this case, we are going to get more amount of amyloid fibril formation. While if we are going above 2.5 millimole concentration of the SDS, so in that case, it is going to change from the F form to F prime form. A similar case is being observed for the SDBS. In my result, I didn't discuss about this part. Although we have performed the experiments, I'll explain you why I didn't put all the data. So likewise, as I said that we have taken all the 5 albumins at pH 3.5. In a similar way, we have taken all the 5 albumin at pH 7.5 also. And under this condition, the albumin, all the 5 albumins, they are going to acquire a negative charge. And since this is a negative charge detergent, so this is not going to make any significant change in all the spectroscopic parameters. So it is because of that we haven't shown the data, and most likely the detergent, they are going to get orient like this, because they are not going to feel comfortable to neutralize interact with this, because there of the charge repulsion, they are going to sit like this. So from here we have concluded that it is a electrostatic interaction that is playing an important role, followed by the hydrophobicity. Now, further, what we have done, that we have taken a lysozyme. Till now, we have talked about only one part, that if somehow we can go below pi, and that case the protein is going to acquire overall positive charge, and then we are going to add anionic detergent, we get the formation of amyloid. So by this, we have shown that we have got different number of publication. So we want to look the other side also. So if you go above pi, so whether in that case the cationic detergent, they also going to lead to the formation of the amyloid. So the best protein, again, it's a lysozyme, and the pi is around 11. And what we have done, we have performed the experiment at pH 9, which is 2 units below, and pH 13, which is 2 units above. So at this pH, the lysozyme, it will be acquiring a overall negative charge, and at this pH at 9, the lysozyme, that will acquire a overall positive charge. So here we are going to add the anionic detergent at pH 9, like SDS and OT, and for the negative charge species, we are going to add a cationic detergent like D-tab and C-tab. These are the structure of the detergent, like SDS, it's 12 carbon, AOT is 20 carbon. These are the anionic surfactant, and cationic surfactant, that is D-tab and C-tab. You can see this is 12 carbon and 16 carbon. Now let's see what is going to happen. The upper panel is at pH 9, and the lower panel is at pH 13. And this is the turbidity measurement that is being performed. And you can see the AOT, which is 20 carbon chain length, it shows a maximum turbidity at 1:10 cubic. And likewise, in this lower panel, it is a C-tab, which is 16 carbon chain length, that shows a maximum turbidity. A similar pattern is being observed for the Rayleigh scattering also. Then we measured the TST binding. Here you can see the order of the magnitude that we have observed, that is being correlated with the chain length. So here you can see AOT followed by C-tab, SDS, and D-tab. A similar pattern is being observed for the Congo red also. Now here you can see this is the data that is being summarized over here. AOT, this gives a maximum redshift. So this is having a 20 carbon chain length followed by the C-tab, then SDS, and this D-tab. ITC experiment there that were being performed at pH 9 and 13 in the presence of the cationic and anionic detergent, just to find out what type of the interaction that is being taking place. So from here you can see the first enthalpy that is coming out to be negative, and second enthalpy delta S2 that is coming out to be positive for all the 4 detergents that were being taken. So this confirmed that the first interaction that is taking place between the protein and the detergent, it's electrostatic, followed by the hydrophobic. Now these are the AFM images, TEM and fluorescence images. You can see in the presence of AOT, we get a maximum amyloid fibril formation. Now this is the summary that is being shown. Now lysozyme is being taken at pH 11, and at pH 9, it will be having overall positive charge. And then if we are going to add anionic detergent, so it's going to interact with this, and this may lead to the formation of the amyloid. While here, this is at pH 13. This is 2 units above pi, and the protein, it will be having overall negative charge. And if we are going to add a cationic surfactant, so in this case also we get the formation of the amyloid. Now we'll come to the therapeutic strategy. So we are working on the inhibition of the amyloid fibril formation by the small molecule. So I'll come directly to that part. So our lab is we have already reported the effect of the vitamin A, B, 12, C, K, taurine, thymoquinine, and several other compounds, and several drugs also. These are some anti-tuberculosis drugs. So I'll come very quickly to this part. So regarding the inhibition. So this is a study that has been published in Scientific Report in 2016, where we have first time we have reported the inhibition of the amyloid fibril formation by the vitamin K3. And the protein that were being taken, it's hen egg lysozyme as well as A beta 42. This is the structure of the vitamin K. Now, these were the aliquot that were being incubated at pH 7.4 for 120 hours at 65 degrees centigrade in the presence and absence of the varying concentration of the vitamin K3. Likewise, the experiments that were being performed with the A beta 42 also. Now, this is the TST fluorescence. You can see there is a steep decrease in the TST fluorescence that may take place once we are increasing the concentration of the vitamin K3. So the midpoint is 50, going to slope off at 100 micromoles. Then we perform a kinetics. This is in the absence, and this is in the presence of the 50 and 100 micromoles of the vitamin K3. So you can see there is a steep decrease in the kinetic curve also, and we measure the TST fluorescence of these. These are the spectrum of these 3 points, and this is a Congo red. This is Congo red alone, and this is the amyloid, and this is in the presence of 50 and 100 micromoles of the vitamin K3. So you can see it's going to approach towards the free Congo red. So this shows that by taking the 100 micromole concentration of the vitamin K3, it shows a inhibitory effect. A similar pattern that is being observed for the A beta 42 also, where you can see there is a steep decrease in the kinetics as well as in that this TST fluorescence. Now this is the ANS banding. You can see the hydrophobic patches. They are being get decreased in the presence of the this 50 and 100 micromoles of the vitamin K3. Here you can see this is at the room temperature. Here we are more interested in the insect because this is the amyloid and this is in the presence of 50 and 100. So you can see there is a reduction in the beta structure that is taking place. So this indicates there is a inhibition that is taking place. Now this is the DLS experiment that is being performed. This is the control, you can say. Here we have taken a lysozyme at 25 degrees centigrade. So you can see the hydrodynamic radii that is going to come around 2 nanometer. And in the presence of 50 and 100 micromoles of the vitamin K3, the hydrodynamic radii that remains same, almost 2 or 1.8, it's almost same. While once we incubate the lysozyme at 65 degrees centigrade for 120 hours at pH 7, so in that case, we get the formation of the aggregates. And here you can see the hydrodynamic radii from 2, it's going to get to increase to 400 nanometer. And in the presence of 50 micromoles of the vitamin K3, from 400, it's going to become 60 nanometer. And in presence of 100 micromoles, it's going to become 40 nanometer. So this indicates that in the presence of the vitamin K3, it's decreasing the hydrodynamic radii of the protein. Now the MTT assay that is being performed for the hen egg lysozyme as well as the A beta 42, in the presence of the 50 and 100 micromoles of the vitamin K3, you can see here it's showing a cytotoxicity, while in the presence of the 50 and 100 micromoles, the cell viability that is going to get increased for the lysozyme as well as for the A beta 42. Now these are the TEM images for the lysozymes that are being shown. This is the lysozyme at room temperature. It doesn't form any amyloid. This is being incubated at 65 degrees centigrade for 120 hours. So here you can see it forms amyloid. This is in the presence of 50 and 100 micromoles. So you can see the amyloid fibrils, they are being inhibited. This is a beta 42 control, and this is the amyloid fibril, and this is in presence of 50 and 100 micromoles of the vitamin K3. So from here we can conclude vitamin K3 inhibits the aggregation of hand-egg white lysozyme as well as a beta 42. Vitamin K3 reduces the cytotoxicity. This study helped us to design a rational molecule for the treatment of amyloid-associated disease. Now, this is a very interesting finding. Because India is the country where we get a lot of patients, they suffer from the tuberculosis. And most of the patients, they take a tuberculosis drug. So keeping this point in mind, so if the person is taking a tuberculosis drug, and if somehow it's going to work in a two-way, that is also going to inhibit the amyloid fibril formation, so that will be a very interesting part. So we have observed that two drugs that is being very commonly used in India, that is pyrazinamide and D-cycloserine, which shows a very pronounced inhibitory effect for the inhibition of the amyloid fibril formation. And this is a study that has been published in PLOS One in 2015. Now I'll skip this part because this protein I have already discussed. These are the two drugs. A is pyrazinamide and B is D-cycloserine. Now here you can see this is the turbidity measurement that is being performed. And now this is the point that is being taken for the inhibitory purpose. Now this is having the maximum OD is around 0.6. So now from here we have added a pyrazinamide. You can see varying concentration of the pyrazinamide, and you can see at 500 micromoles of the pyrazinamide and D-cycloserine, it becomes plateau. So from here we can conclude that pyrazinamide looks to be more pronounced, showing an inhibitory effect as compared to D-cycloserine. Now we perform the TST fluorescence kinetics also. This is in the presence of 125, 250, and 500 micromoles of D-cycloserine, and this is pyrazinamide. So from here you can observe that there is no significant decrease in the is being observed as compared to this one, pyrazinamide. So you can see there is a steep decrease in there. And these are the spectrum that are being shown for these points. And you can see there's a significant decrease that is taking place in the presence of 500 micromoles of the pyrazinamide. That shows a pronounced inhibitory effect. Now this is a congruent again. This is in the presence of D-cycloserine, and this is in the presence of the pyrazinamide. So it's going to inhibit. And this is ANS binding. And in the presence of pyrazinamide, you can see it's diminishing the ANS binding, while in the case of D-cycloserine, it's not so effective. Now, this is the fluorescence images that are being shown. This is the control, and this is in the presence of pyrazinamide as compared to 500 micromoles of the D-cycloserine. Now, this is an MTT assay that is being performed on PC12 and SHS5 5' cell line. This is the control. This is hand-egg white lysozyme fibrils. So the cell viability that goes down. And in the presence of the 125 micromoles of the pyrazinamide, you can see the cell viability is being restored. It is more as compared to 125 micromoles of the D-cycloserine. Likewise, here also in the presence of the 500 micromoles of the pyrazinamide, it's more effective as compared to 500 D-cycloserine. This is the overall scheme that is being shown. We have taken lysozyme, which is being incubated at 65 degrees centigrade for different time, 120 hours. And in the presence of the D-cycloserine and pyrazinamide, it's going to inhibit the amyloid fibril formation. While if you are going to incubate it for 120 hours at 65 degrees centigrade, so it leads to the formation of the amyloid. So pyrazinamide is a strong inhibitor as compared to D-cycloserine because it's prolonged the nucleation stage of the amyloid aggregation through binding to the region of the protein, which is known to form the core of the protein fibrils. Now, this is another anti-tuberculosis drug, capromycin, which is being taken. And this is a study that has been published in BBA in 2018. And here the protein that is being taken is bovine insulin, which is 51 amino acid residue long. And this is responsible for the glucose metabolism. And capromycin is a peptide antibiotic used for the treatment of the tuberculosis. So we are more focusing on the anti-tuberculosis drugs also. So now this is an insulin that is being taken, which is being incubated for 72 hours at 60 degrees centigrade at pH 2. That is to the formation of the amyloid. And we just want to see how is the capromycin is going to inhibit the amyloid fibril formation by measuring the TST fluorescence. Now this is the control. Here you can see this is showing a positive TST binding. As we are going to increase the concentration of the capromycin from 10 to 200, you can see the inflection point is around 75 to 100 micromoles. So these were the points that we have taken for the kinetic measurement, 75 micromoles and 100 micromoles of the capromycin. You can see this is a kinetic curve that is being observed in the absence of the capromycin, and this is in the presence of 75 micromoles, and this is in the presence of the 100. So you can see it's a very sharp, steep decrease in the kinetic curve that is also being observed in the presence of the capromycin. Now, what we have done, we have added this capromycin lag phase and midpoint of the log phase, 100 micromoles. We just want to see how it's going to inhibit the TST fluorescence kinetics. So you can see once if we are going to add after 8 hours, so you can see it's going to follow this type of kinetics. And if we are going to add them at the midpoint, that is around 18 hours of this, so you can see again it's showing the inhibition. Now these are the time images that are being shown. This is the amyloid, and this is in the presence of the 75 and 100 micromoles of the capromycin. Now here what we want to see that once the amyloid fibrils they are being formed, so can we disintegrate the amyloid fibrils by adding the drugs? Although we have shown, I'm not discussing in this part, we have published this data that vitamin C, vitamin B12, they show that once the amyloid fibrils, they are being formed. And if you are going to add the further higher concentration of the vitamins, so in that case, the pre-formed amyloid fibrils, they are going to get disintegrated. So here you just see that this is the amyloid fibrils, they are being formed, which is being measured by the TST fluorescence. Then what we have done, we have added a capromycin at 12 hours, 24 hours, and 48 hours. So you can see the TST fluorescence that get decrease at 12 hours, then 24 hours, and 24 hours and 48 hours. It's almost no significant difference that is being observed. But from here you can see there is a steep fall that is there. This is the insect that also shows that. Likewise, we have performed a hemolytic assay just to see how it's going to disrupt the cell viability. So this is a bovine insulin fibril, and this is being taken along with the capromycin, 100 micromoles capromycin at 12 hours, 24 hours, and 48 hours. And these are the amyloid fibrils time images that are being shown. Now you can see this is the time. Here we get the amyloid, and this is the time image of this point. So here you can see which is being incubated in the presence of the 100 micromoles of the capromycin for 48 hours. So we get the disintegration of the amyloid fibril formation. So from here we can conclude that capromycin suppress the insulin fibrillation and possess a destabilizing effect on the mature insulin fibril, and it is effective in blocking the fibrillation during elongation phase. So this is an incomplete list. So this is the overall achievement that we have made during the 2 decades. We have published more than 340 publications. This is not updated. I'm sorry for this. And I have supervised almost 23 PhDs scholars. I got a funding from DBT, DST, CSI, UGC. All of them, they are very good funding agency from the India. My citation is around, this is around 13,000 now. And I'm a visiting fellow to University of Michigan, USA, and University College London, UK. I'm an editor of several journals. And this is my group. Dr. Javed has done most of the experiments, Sumit. And I would like to thank DBT, DST, CSR, UGC for the financial support. Thank you for the listening. Thank you for your attention.
Okay, thank you very much. I don't know if somebody in the audience have any question. You can write them in the chat or unmute yourself and ask them through the microphone. Okay, so no one?
I have some questions. So hi, I am Salvador Ventura. Very nice talk. I mean, very clear and biophysically very sound. So my question is that in the last set of experiments you have shown, you have using conditions that's very far away from native conditions. Okay, so you are using extreme pH or you are heating the protein. So how your data relates to what happens in the body? How physiologically relevant do you think your inhibitions with vitamin or anti-tuberculosis compounds or the assays with SDAs are? Because you are very far away from the native conditions and you're not taking into account which is the protective role of the tertiary structure. Can you comment on that?
Yeah, it's a very interesting question. I appreciate that because most of the time we get the same comments from the editor also or reviewers also. So the study that I have shown over here, it's really, I'm sorry that I didn't show my all the data. Regarding the vitamin C and some other naturally acting compound, we have taken a physiological pH and physiological temperature, so that we can justify the data. Even the concentration of the drugs or the vitamins that we are taking, it's the same concentration that is being recommended by the doctors or the concentration that is we are taking in the food. Say for instance, the vitamin C. So it is 50 micromoles that is there. So we have taken whatever the concentration that is being reported in the literature. So we were below and above that. And the pH that we have used for those experiments is around pH 7.4, and the temperature was around 37 degrees centigrade.
But in reality, when you show lysozyme, you use 65 degrees. When you use insulin, you go to pH 2. I am wrong with that?
No, that's correct. In lysozyme, it's you know that it's you are also working in this area, so you have a extremely good idea about that. So lysozyme, it's a very rigid protein, so it can form say amyloid under very harsh conditions also, even at pH 7 also. So, but you are supposed to manipulate the ionic strength or something that. If you want to work at pH 7.4, even in that case also, but you are supposed to give a long incubation time.
Okay. Oh, no.
Yeah, so that means you are supposed to wait for 15 days, something like that. So in that case, you can observe the things in that case also. But here we are just hastening the process just to get the data within a week or something like that.
No, I mean, I'm not saying it's wrong. I mean, we are doing the same because there are proteins that you have to unfold. But then you also know that the aggregation pathway could be different and the intermediates could be different. And this is our case. I mean, some drugs that will work in harsh conditions, they will not work if you go to the formation of, let's say, long-standing oligomers. And we have some expertise with us. We have drugs that work in accelerated pathways, but then when you use in native condition, they don't work that well because they recognize protofibrillars structures.
Yeah, I agree with that because tertiary structure is very labile. So if we are going to change the pH, so we most likely we are going to lose the structure, and we are not going to near about the physiological condition. I agree with this.
Yeah, I know. So thanks a lot. It has been very nice to listen to you.
Yeah, thank you. I'll be happy to have a collaboration with your group also.
Good. We can talk about that later on.
Okay, thank you.
Okay, thanks. Is there any more questions? No? So if that's not the case, we will stop here. So thank you very much, Ken, for your nice seminar. And we hope to be in contact for future or present possibilities in collaboration.
Sure. Thank you.
Okay, thank you.
Thank you. Bye.
Thanks a lot. Bye.
Thank you. Bye.
Bye-bye.
Bye.
Bye. Thank you.
Bye.